accepted.
So, welcome to not quite the last one of the day, though amazingly I'm doing another talk after this as well, so you can just sit tight, because we're in the same space. I can't really see you, so I'm going to assume that most of you are Java programmers. Yeah, because you're at Devoxx Poland, so let's assume that. Okay, so I'm going to talk to you about what it says, hidden security features of the JVM, and if I'm really lucky, you'll have known most of them. So my name is Steve Poole. I work for a little company called Sonatype. I'm the director of developer advocacy, but mostly I'm a JVM developer at heart, and I've done a lot of open source over the years. Been doing this for a long time. So lots of Java and JVM background, lots of Java background, so been around the block a bit. So I work for this company, which you may or may not know, but we're the people behind this thing. Hey, Java programmers, who uses Maven Central? Okay, yeah, yes. If you're a Java programmer, you don't put your hand up. You probably don't understand what I'm saying. So Maven Central, we do that, and the other stuff that we do, Nexus and a bunch of other stuff, right? So the interesting thing is I will talk a little bit about supply chains, because we need to talk about the security features in context, but most of this is a JVM talk. The one thing it's not about is this thing, the security manager. A long, long time ago, there was a need for security in Java, and we went about adding it in probably the worst way we possibly could, and that was by adding in this security manager that you can configure capabilities, and you could check whether you had authority to do stuff, but it was a bit of a pig, and pretty much nobody's ever used it. So if there's one thing that we've all loved to see deprecated, it was the security manager. So we're not talking about the Java security manager, we're talking about some other stuff, right? Oh, and we're not talking about some of the other replacements that came along. So there's some internal bits and pieces that have happened to give us, as it says, strongly in caps internals, and there were some extra bits and pieces, right? But they're not really for us, or for you as developers. They're much more what was happening on the inside. Because if you put up the words that you can go find out when you go to OpenJDK, and you talk about the Java platform, actually, as you're going to see, it's very secure, for some level of very. And they have a bunch of words in there that says, we do this, we worry about the integrity of your data, we worry about the confidentiality of your data, and we're always trying to keep security up to scratch. So don't worry about reading the words, but this is the intent. The intent has always been that the JVM is as secure as practicable. So I'm going to touch a whole bunch of stuff. I'm going to have to start off with talking to you about why this is even important, and about the types of attack we're going to get, and talk about what a JVM is, and some of the inherent characteristics, and then I'm going to talk about some other secret weapons that you probably haven't even thought about, and then we'll wrap up. Okay, so let's start here. What's going on? What's the situation? What's the point of having security? Is you have security because there are people out there who want to get in and steal your data and install ransomware and malware. You know all the things, right? Okay. So it's not good. When I first started talking about cybercrime, because I used to run I used to work for IBM, and I ran the European DevOps team. And as a developer before then, I wasn't really interested in security, but when I took over the DevOps team, suddenly I understood why it was important. And about that time, I thought if we should be communicating to developers what the problem is. So I would go out and come and stand here and talk about these things. So 2016, the amount of money the bad guys made from cybercrime, just a tiny bit, became more than they were making from the drug trade. So you think about this. You've all seen those wonderful movies about the drug trade. You know, we've all seen the fun ones and the bad ones, but it's enormous. You know, do you think how big it is? And when you sum it up for the world, and you estimate, it's $450 billion, or it was back in 2016. Right now, it's a little bit more than that, but it's okay. It's controllable because it's physical. Right? Cybercrime isn't physical, and in 2016, it just made a bit more money. So to put that into physical things, there's a number there. So you could buy, if you could get all the money together, 50 US Nimitz-class aircraft carriers, because actually they tell you how much they're worth. So you could buy 50 if you had $450 billion. Okay, so that's an enormous amount of money, enormous sort of things you could do with it. But if we come to now, we fast forward a few years and we say, how has this changed? Well, the drug trade is still about 450-ish, goes up and down a bit, because as I said, it was physical, it's manageable. You can see drugs have to move. Cybercrime, there's nothing physical, it's digital. So it scales, right? 2023, 11.5 trillion. Think about that. I've gone from 50 of these US carriers to 1,120. It's like 23 times. So the drug trade has grown, the cybercrime has grown 23 times since 2016, though the drug trade has carried on. There is no sign of it stopping. If you take that number, can you imagine $11.5 trillion? Can you imagine 1,000 aircraft carriers? Where would you put 1,000 aircraft carriers? Okay. But can you get your head around that? Well, let me put it into context. If you could get all this money in one place, and you said, how does that match, say, the gross national product of a country? Right? Because this is country scale money. It turns out it would be the third largest country in the world. So cybercrime, get all the money in one place, would be the third largest country in the world. That's pretty scary. So that's why this is all very serious, because of this scale. And there's no sign of it stopping, right? It's just been growing at about 56% per year, right? And it carries on. There is absolutely no sign of stopping it. And the way things are going, it's going to eclipse the US GDP. That's how much money is being stolen, how much money it's costing us. It's a complex equation, but it affects every single one of us, one way or the other, and it continues, right? So, as they say, if Escobar was around now, he'd be using a laptop. He wouldn't be doing drugs, because cybercrime is the most profitable way of making money, illicit money. It's almost impossible to get caught, and it is growing and growing and growing. Okay? So there's the context. This is a serious subject that you have to get your head around. Now, how does that then connect? Well, what are the bad guys doing as far as we're concerned? What's the vectors? How do they get in? And we'll talk about that in detail. But the thing you have to understand is a lot of this comes from open source. 90%, or 95%, or 85%, pick a number in that area, of the application that you produce is built on open source dependencies. So 90% of what you write, of what you've produced, is actually, you produce 10% of it, somebody else produces the other 90%, and it's shared. So that's the vector. These bad guys are trying very hard to get into these open source projects and steal them and steal them and corrupt them, add malware, take them over. We have so many examples of this happening. It's active and it's happening now. Okay? So it's become so important that the governments are trying to do things to prevent this, and you'll see a whole bunch of laws and things coming down. And if you come to the talk after this, we'll go into that in more detail, because we'll talk about supply chains. But basically, you have to understand there's some big bad wolves out there, and they're out to get us. So it's important to understand how they might attack you, and because of the JVM talk, we'll talk about this from a JVM point of view. But the one thing I want to leave you with is that there's no time. It used to be you have days before the attackers would make use of exploits. But these bad guys are creating their own ones, and they don't get noticed. And right now we're in this world of exploit first. You will know about a problem when it's too late. So that's the world we're in, much scarier than we used to be. So let's look at how they get in. What's the JVM side of all this? So obviously we'll look at attack vectors, but to look at attack vectors, we have to sort of look at the big picture, the very big picture. So the yellow box is the Java code. Obviously the application code is your code, and then the dependencies is the big box that we're all borrowing and sharing. And then underneath that, there's other code. Remember, this is all targetable. So how do they get in, right? If you think about what a JVM is, there's obviously the system classes, there's the JVM, whatever that is. We'll talk about that in a minute. There's a compiler, there's a Java compiler, there's a JIT compiler, there's JNI, there's class libraries, there's native code, there's all sorts of places. So hopefully all this stuff is knitted together to give you some safety. So the obvious first place they're going to try and get into is communications, because they're remote. How do they get into the Java system? How do they get into a JVM remotely? Well, we talk about compromised communications, but actually, if you look at what is happening in the JVM space, and has always been going on, the JVM and the Java space, the OpenJDK space, keeps up to date with the latest security protocols as much as possible and as fast as possible. We have enormous choice. You can go Google for all this stuff. So it's good. We have good, strong support. There's no particular reason to worry about that, provided you use these things. Okay, so we can tick that one off, right? So if they can't come in remotely, where else can they come in? Well, the other end is the whole other end of the thing. So you've got your JVM, you've got your application. What else would they try and attack? Well, they'd like to get into the external environment, the piece that you expect to be there, your Docker container, your VM, your terminal. This is an environment that they run in. So what are the bad guys trying to do? Well, they like to get in and change things. So environmental variables. So now, I should get rid of a myth. There is this idea that if the bad guys can change one file on your system, they can change everything. And that's not true at all. There are many, many instances of vulnerabilities that allow very specific or very controlled files to be changed. So don't ever think that if they can change one, they can change everything. That's the wrong way to think about it. Think about it as just a tiny sliver of access, a letterbox they can get into. So if you think about what they could do by getting through that letterbox, there are environmental variables that could be changed that will affect the way that you run. They could, for instance, play around with the environmental variables, turn off verification. Talk about that in a minute. Okay? The first takeaway, and it's an unpleasant one, but it's true, is the JVM assumes that it's running in a safe environment. So it's up to you to make sure it's a safe environment. JVM really can't do much more. Okay? So communications is covered, but environment isn't. Environment is your problem. Okay. So what other attack vectors are there? Well, you can start pulling this model apart. They could change the bytecode. They could get into those class files that these open source projects that are in your dependencies, and they could change them. Yep, that's very true. They can change the open source code. Can they change the bytecode inside the JVM when it's running? We'll touch on that one. Can they corrupt the heap? Can they get in there and do bad things? Is that possible? Okay. How about loading bad code? Well, there's possibilities. So we'll look at some of these things. To answer the questions, though, to start looking at this in detail, you have to sort of go down a level. And so you have to look at something that maybe you haven't done much with, which is work out what it is that a JVM actually is. So let's have a look at that. Let's look at what a JVM is. Okay? So lots of words on the internet. It's a virtual machine that enables a computer to run Java programs, blah, 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 other programming languages. It's a virtual machine, right? And you know all this because you make use of all this stuff. It's dynamic, it's predictable, because you can run Java anywhere, Wara. So the JVM does that, provides you that environment. So when you start piecemealing it, and going, what are the pieces here? You can start off with a bigger picture. So here's my bigger picture. Application, and there's a JVM, and then the JVM has to deal with all the different operating systems, all the different hardware. It has the different windowing systems, whether it's Windows or X or whatever UI system, different file systems, networking, has to deal with threads. It's all this stuff that we go, well, the JVM does that. But as you're going to see, that's not really true. But that's the biggest picture. Right? So this is the stuff you have to start thinking about. Where's the security stuff in this piece? Right. So we step back more, and we have a slightly better abstraction. Right? So, let's just generalize this. You have an OS layer, and you have compiler, and you have class loaders. You all know about class loaders, and some code. Some native code and some Java classes. Okay? And you can take that out a bit more. Because actually a JVM, if you go to the specification for the JVM, it's even smaller than that. The JVM spec says it's got a memory model. It talks about CPUs, what a CPU model it is. It talks about a threading model. And obviously then there are these translations from whatever the Java model is into whatever the operating system needs. It might be taking bytecode and turning it into machine code. It might be coding into native code. There's always some of that. Okay. Well, actually, even this picture is too sophisticated. Because if you boil it all the way down, the specification doesn't talk about threads. It has a concept of locks, critical sections, but there's no specification of what a thread is. There's no specification of memory. JVM doesn't know about garbage collection. It doesn't know about heaps. It just knows about object references. And its view of what a CPU isn't anything like you'd be used to in terms of, I don't know, if you look at Intel machine code or ARM machine code. It's a completely different, very, very, very simple stack-based model. So in some ways, we're actually lucky to have this because this specification is the sort of thing that you need to break out of to do bad things. And this specification is very, very simple. So there must be some other magic involved. Hey, there's some more magic. Right, so the first line of defense of all this is this idea of the JVM being a very, very simple CPU. So that spec gets translated into machine code that your JIT will run, and that's the idea. So we have a specification of a stacked-based machine with one program counter, and even the program counter, if you've ever done any assembler, you have registers and you can set values. The program counter just keeps track of which line of code to run, but even that is not really affectable. So there are no pointers to forge, because there's no memory. It's all object references, right? There's no way of breaking out into the host environment. There's nothing in the specification that can allow you to escape. And the only thing that's making this specification real is really the JIT and some of these supporting libraries. So we have a really good sandbox because it's very, very simple, and it's basically impossible to break out of. So that's good. So there's more, because there are these unspecified things. So if you're ever feeling like it, I encourage you to go look at the JVM spec, and that will have links off to other bits and pieces, and you'll be able to trace through where things are defined. And one of the things you'll find interesting is that the thing that we use, the Java, the specification for the Java environment, isn't in one place. It's spread all over the places, and some of the spec is just in JavaDoc in class files. And some of the spec is defaulted to whatever the operating system decides. So it's all over the place. But because of that, it means we're allowed to do things with Java that the spec doesn't care about. So we have garbage collection. We have threading. They are implementations that were chosen that, in theory, you could do differently. You don't have to have garbage collection. You could have an infinite amount of memory, right? But the fact that we have garbage collection is a second line of defense, because one of the ways that bad guys like to get into your system is to look at your memory. And if they can look at your memory and you have a consistent use of your memory, then they can find passwords or critical data because they know where the objects are. Garbage collection is moving that stuff around all the time. Right? So the ability for the bad guys to just drop in is greatly reduced. Okay? So that's a significant plus for us, even if it's sort of a side effect. Now, the threading model, as it says here, is there's a leaky thing with threads. So you imagine we have no idea, threads are not part of the spec, we create threads, we'd like to keep them abstract, but for historical reasons, there were places where threads had to know about real life. And when you get virtual threads, even that leaky spot which could be exploited is gone, because virtual threads have no way of knowing about the outside world. So if there's no way of knowing, they can't be compromised. So another tick. Another unspecified feature that we rely on is the JIT. That thing that compiles machine code, the bytecode to machine code. We couldn't do without that. It is integral to how we live. Right? But the fact is that what it does is not always predictable, because what JITs do is they look at what's going on now, they look at your code, they compile based on now, and they may change their minds. And what they compile could be subtly different from tomorrow, or in 5 seconds, and they may change their minds again. Okay? And it also, because it has a security hat on, also understands that it's not good to allocate memory in the same place over and over again. So it too has random allocation built in, right? So the bytecode that might be subverted, and it is possible to subvert bytecode as in write your own, the ability for that bytecode to be executed as is unlikely. There's a whole bunch of stuff going on that says you're going to be safe because the JIT is getting in there first. And we'll talk a bit more about what the JIT does in a second. Okay? So what you have to get is the JIT is another line of defense because it's dynamically generating code and objects in terms of where they lay out on a random point-by-point basis. And if JITs have access to machines that have read-only, read-write memory, they can make those choices too. So they can actually, if they need to, put objects into read-write, read-only space. The bad guys can't change that either. And then this bytecode I keep talking about, it's a great defense model too. Because it's very simplified, it's a stack-based machine, unlike pretty much everything else we use. Right? It's very hard. There's nowhere in this sequence of bytes that means you can escape. And I said you can't forward pointers, so you can't wander around the heap. You have to have an object. And then you have to go to another object, and then you have to go to another object. So it's impossible for you to just wander around, right? And because the JIT is turning that bytecode into machine code, it's got to be comfortable that it's going to work. I mean, not just do what you want it to do, but it's actually going to be compilable. And that it's actually not going to break some of some potential constraints, like run off your heap or run off your threads, blow your thread stack, do a bunch of stupid stuff. So there's built-in verifiers that all the time work out whether the bytecode that you've written or your compiler's generated for you is actually going to be safe. Because we understand that there might be weaknesses that could be exploited. But the first level is, does it actually comply with the spec? And when we do that, we're doing this when you load the class off the disk. Is it properly structured? Does it look like it's properly, is it going to behave properly? Right? And then at compile time. So it's really hard to forge bad bytecode, let alone the fact that actually the bytecode themselves are particularly simple. So third line of defense. Right? So there's a bunch of stuff this verifier is doing, wherever it does it, whether it's loading time or compile time, and it's always trying to check, because we're concerned that it could break. There could be a vulnerability and there could be a weakness in there. So there's always this idea of proving, as much as we can, that this bytecode is going to be safe, right? And you can see like access controls and stuff like that, because it's always the worry. But there's a bunch of proof, right? So that then says, so, okay, bytecodes are safe. Where does the bytecode come from? Well, from class loaders. Class loaders are great, as long as you don't have too many of them. Certain application frameworks we might be able to name got a bit carried away, but in general, class loaders are, again, another safety mechanism. The idea is that class from a particular class loader can't interact with other class loaders, depending on the hierarchy. And it allows us to add extra checks, like if we know we're loading remote code, we can be more thoughtful about what this code can and cannot do. We put a sandbox around it. Okay. Unfortunately, there aren't that many class loaders, so the idea of being able to structure your application and have lots of little class loaders, which was an idea at the beginning, has turned out not to be the greatest idea because you have to manage this. So generally, you probably only have 3 or 4 of those. And those ones, the bad guys will try and subvert by getting into your environmental situation and maybe trying to add jars to your class path on any of these things. So that is a weakness. Nothing we can do about it because we're relying on you to provide the environment variable, the environment space, right? But class loaders are another defense mechanism to allow us to separate code from different sources to make sure that if we do get bad stuff in, it's got less chance of causing damage. Now, loading remote code has been there since the beginning. It's sort of like one of the reasons that Java was picked all those many years ago, was the idea that you could just run code off the internet. Anybody got a guess what this little substitution parameter looks like? Log4j. Yes, everybody's heard of log4j or log4shell, okay? So this is bad, and this was bad because this isn't a JVM thing. We just went up and invented the idea of having these special objects, remote reference objects, that not only can be loaded remotely, but can also tell the JVM, or the class loader, where to get the rest of the code. So you know that normally the code that runs is on your class path. There's nowhere else for code to come from, right? But this thing, this reference object, is really clever because it says, here's me, and anything that I reference should come from this URL. And if you happen to have that log4j vulnerability enabled, this was a really great way of getting arbitrary code into your system. I've got some great demos, okay? So class loaders are great for separation, provided people don't get too enthusiastic, J and DI, and don't think through the consequences of what they're adding. But that's not really a JVM problem, is it? It's an unfortunate side effect of a lot of people being very enthusiastic about adding features. Okay. Ooh. That was cool. All right. So, remote code. Okay. J and DI. What does that say? That says serialization. Let's talk about serialization. Well, serialization is one of those things that wherever you are, you can't avoid it. It doesn't matter. It's everywhere. Serialization is so fast, so easy to use, such a wonderful way of being able to move Java objects from one system to the other, that it's there. I mean, and they turn up. They get used to store data in. They get stored in cookies still, all sorts of places where Java objects, graph objects get stored, right? And it's a nasty thing. And all of you know, because I'm sure you've all seen the talks about serialization. Brian was doing one earlier today, just how dangerous it can be. And the problem is, this is everywhere. If you go to GitHub now, and you do object input stream, which is the class for loading stuff, you get, what was that, 3 million hits? That's just on GitHub. So it's everywhere. And the problem with this is, so this is the weakness that we have. It's probably the biggest weakness in Java that everybody just wishes we hadn't got here. But there are good reasons why we started down this route. So look, if you look at a serialization stream, and this is a table form, because obviously it's a byte sequence, there's some stuff on there. Look, there's a field type, L, which means object, and then there's a field name, which says hello, and then there's a class name, and then up to the bottom it says string value. So at first glance, it looks like you're going to load, in this example, you're going to load the value called hello into the field name called hello that's of type string. But it doesn't mean that. Serialization data is self-defining. So the name of the field and the type of the field, so the name of the field in the object that you're putting some data in, and the type of data you're bringing out, you're loading off this serialization stream, are unrelated. This is the biggest problem we have in security, really, on a day-by-day basis with Java, is this little problem. Right. So that's the name of the field in the target class, hello. That's the definition for the serialization process that says what's about to follow is a string. It doesn't say the field called hello is a string. It doesn't do that. It doesn't know until the last minute. It doesn't care. So that means that you will find that serialization forms can be subverted by the bad guys. And so you'll have little snippets. So look, you could put a string with a value of hello. I could put an array with a value because it's self-defining. I can put that in the data stream. I can call it an int. I do whatever I want. And I can put that data in this serialized form and send it to your JVM. And your JVM will very dutifully load it and then try and put it into that field. And depending on whatever field type it is, it may or may not fit. If it's, say, int and you've got an object, it won't work. If it's a string and I give you a string, it will. If your field type is object, then pretty much I can put everything in. But the bad thing is not just that I can put anything, or I can attempt to put anything in. The bad thing is that object gets instantiated regardless. So that means that object got created regardless of whether it's going to fit. And as soon as you instantiate an object, code gets loaded and run. Okay? So that ends up being a bad thing, which I'm sure you already knew about. So serialization, still a problem for us. And wherever you go, implement serializable with the little tick that gets you into this game, 15 million on GitHub. Okay. And reflection is another tool that gets used to do this. So I said about loading up serialization that this allows the bad guys to instantiate an object. That allows the object to instantiate others. That thing could be a chain of these things. It's called a gadget chain. There's an example of one, which gets you from object input stream at the top all the way around down to runtime.exec. That's what the bad guys are trying to do. And that's, unfortunately, quite feasible because we don't really have a defense against it. And if you think it's hard to do, well, yeah, there are tools out there that will help you create these things. So, having told you a bad thing, are there some good things? Well, there's some defenses. There's class filtering. Let's do the next one, it's probably better. Java 17, we added some features that means that you can set lists that you have classes that you will allow. So when some arbitrary thing instantiated, you can say, yes, I will allow that in, or no, I won't. But it's pretty big stick. But it's definitely a solution. Okay. Another way around this is to use modularity. Because apart from the JNDI thing, what are the bad guys trying to do? They're trying to load code. Where's the code? On your class path. All of your class path is available to it, unless you use modules. Because modules separate these things. Cross-module access is restricted. We don't have blanket access. Okay. Now, you could go even more. You could use JLink. Anybody using JLink? I'd love to know. Anybody actually using JLink? If there's hands up, I can't see them. Yes. But another JLink, the idea of modularity is to remove all the code that you don't need, removes the attack surface. So JLink is a security tool, but it relies really on using modularity and modules, which pretty much nobody does, unfortunately. So if you still don't want to use modules, you could use sealed jars. Now this is a simple thing, which basically says you can specify on the jar, in the manifest, a name of a package, and the JVM will only load code from that that matches that package from that one jar. If it encounters that package, a class in that package on a different jar, it will throw an exception. So it's a good way to encapsulate your code to prevent people maybe trying to replace them. It's an opportunity. If you don't like any of these things and you still need to use serialization, we have records. Records are great because it's just data. There's no code to execute when you instantiate these ones. So you could look at using those instead of having big fat objects that you move around, that you serialize and send around. So you could look at records. And if you don't want to do that, well, you take this class, right? So here's a class with a no argument constructor, and you convert it by adding in code like this. During serialization, deserialization, constructors are never called. And people don't understand that. But a way that you can make sure that your constructors are called is to get dirty with the code and restructure it and have a separate method that initializes your object, and then add that horrible private void read object blah, blah, blah that calls your constructor. That will help make your object a lot safer, but you have to do that for every single class. Because it's a private field, you can't put it in some object hierarchy and have it inherited because it's a private field. So there's your clunkiness. Okay. So other things. So most of the time, the JVM, just its basic design, is reasonably secure. And the main weakness we have probably is serialization and remote coding, loading. And serialization, if you use modularity, the problem gets less. It doesn't go away. We don't have a total solution for that, unless you opt out. How about compiling to native? Anybody on that journey? Anybody here using Quarkus to compile to native or Graal? Go. Are you awake? Go. Okay, so compile to native has been offered as a security benefit because obviously it's not Java anymore, so Java serialization would not work because you compiled it to native, right? So there are lots of pros and cons, as you can see. The downside is that you lose all of the dynamism that you get from garbage collection and like jitting and stuff like that. But it does reduce your attack exposure because you have less code, and of course it's not Java anymore. So that's up to you, but it is a choice. Okay. Now, there are two other secret weapons, which I have 8 minutes to tell you about. Neither of them you've probably thought about. So the first one is this thing, Maven Central. Okay? Look, malware, horrible stuff, it's all over the place. Malware hardly ever gets into Java. I told you about the bad guys trying to attack open source projects, yeah? And they try hard. One thing they don't do, and if you look at the different types of attack that they use, most of these types of attack are not applicable because of Maven Central. So Maven Central requires that you own the domain that matches the package name when you publish it to Maven Central. Now, that little tiny thing means that so many of these types of attack disappear. So you can be reasonably confident that the code that you download from Maven Central is actually from the person who put it there, and that that person is legitimate. There are a lot of other repo systems. Excuse me. It's the fizzy water. So there are other systems out there which don't have that level of protection. But Maven Central is keeping you safe all the time because it ensures the code is legitimate. We've only ever had one instance of malware. One, and all the time. And then you look at all the other repo systems and you can see they have tens of thousands on a very regular basis. Maven Central reduces this, and though you probably don't realize it, because Sonatype is a supply chain company, we scan the heck out of this stuff when it gets added up. So if we can find any malware or any vulnerabilities, we'll flag it. If it's malware, we'll deal with it. If it's vulnerabilities, we'll let you know. Okay? So that means a bunch of these different types of attack disappear. Dependency confusion and typo squatting. Well, typo squatting sort of disappears. Typo squatting is about where they spell the thing wrong and you spell the thing wrong, but it turns out that the mistake that you've made matches the bad code that they put on the repo. Bad guys don't do that for Maven because it costs money. Right? So Maven Central is another secret weapon. One more. That's you. Right? Well, you could be a secret weapon. Okay. You're not quite a secret weapon yet. Log4j. Who here hit the Log4j problem? Who had a great Christmas? Yeah, is that great? Or you know what I mean? Yes, everybody. Okay. So today, pretty much today, 33% of the downloads from Maven Central are still for vulnerable versions. Those bad things. And if you went to Brian's talk, he gave you a really good demo, right? This bad stuff's out there, and 33%. So 1 in 3 of you is downloading bad code. And the thing is, still, after all this time, and the thing is we know, because we have all the data, that pretty much every time a vulnerability is published, there is a safe version for you to move to. But for some reason, you're really slow at making that move. Right. So to become the secret weapon for Java, I need you to change the way that you behave and start looking much more at the choices that you make. And rather than making choices for the feature, start looking at the choices about the capabilities of the people producing the software. Take a moment to go to the GitHub repos or wherever, and have a look. Because way back at this talk, I talked about the cyber attacks and how bad it is, and how they're targeting open source. Well, there's a lot of us out there that are now trying to work out how we identify whether an open source project has the right characteristics. So if you go to Maven Central, you'll start seeing things like Sonatype ratings. Linux Foundation's got them. They're coming out. We're trying to work out how to score this. If you go to Maven Central, there's a link, or you can go to this is a experimental tool that we're putting out, which will let you have a look at this data. What we're trying to do is help you make better choices immediately. Because right now what you do is you pick open source projects because GitHub or Google tells you that's the right answer, and you pick it. You might go check the license, but you probably do not go and have a look at that open source project. And I'm asking you to do now is to start thinking more about that. Because the JVM is pretty solid, barring serialization. And the weaknesses in all of this are turning out to be not in the tech, but in your choices. And what I need you to do is to start thinking more about why you chose something. Because it's so much better to make the right choice now than deal with the consequences on the 9th of December because some big things hit. Because almost always, there is a fix for the thing that you're hitting, and the fix was already out. So that's that. Thank you for listening. Hopefully I scared you a little bit. But also I hope you understand that you're using a really safe platform already, and that many of the problems that our colleagues in different programming languages have don't really apply to us because of the way the JVM is designed and the way that our ecosystem works. So that's it. Thank you very much. I will be around all week. And if you are really interested, I will be here in whatever it is, 15 minutes, talking about securing your supply chain. Thank you.